In this lecture we are going to solve problem 2.8 from chapter 2, the working fluid, and book Applied Thermodynamics by T.D Eastop McConky. The statement of the problem is: calculate the internal energy and enthalpy of 1 kg of air occupying 0.05 cubic meter at 20 bar. If the internal energy increased by 120 kilojoule as the air is compressed to 50 bar, calculate the new volume occupied by 1 kilogram of the air. So first of all, we will write the given data. So we have given that mass of air is 1 kilogram. The volume which it occupies at 20 bar is V1 and it is 0.05 cubic meter. Also, pressure P1 is 20 bar. We can say that this is the state 1 of the air. If the internal energy is increased by 120 kilojoule, so now this is state 2. Internal energy is U2 is equal to 120 kilojoule, and pressure also increases from 20 to 50 bar, and it is P2 is equal to 50 bar. We have to find three things in this problem. First, for state 1 we have to find internal energy, means we will find U1 and enthalpy of 1 kg of air, that is H1. So we are finding the enthalpy and internal energy of 1 kg of air, so this will become U1, small u1, meaning that this is the specific internal energy. Also, the enthalpy which we are finding will be also specific enthalpy for state 1. And for state 2, second, we have to find the new volume occupied by 1 kg of air, that is V2. So coming to the solution of this problem, we will need some other supporting values which are given in the start of the exercise in chapter 2 problems. That is, it is given in the note. We will use the value R, that is specific gas constant or particular gas constant, and its value for air is 0.287 kilojoule per kilogram. Also, if we write it in joule per kilogram, it will become 287 joule per kilogram per Kelvin. Similarly, the value of specific heat capacity at constant pressure is 1.005 kilojoule per kilogram per Kelvin. So these values will be used in the solution of this problem, 1.005 kilojoule per kilogram per Kelvin. Also, the value of CV is 0.718 kilojoule per kilogram per Kelvin. So now to find the value of U1 and H1 For that we will need the temperature T1. So using the characteristic equation of state for the air, that is PV is equal to mRT. So for state 1 it will become P1, this will be V1, and M is constant in both state 1 and state 2. R is also fixed, and this will become T1. So we are interested to find the value of T1 first. So it will become P1 V1 over mR. So putting the values, T1 will be equal to, the value of T1 is 20 bar. So 20, converting bar into Pascal, we will multiply 10 raised to power 5 with this. The value of V1 is 0.05 cubic meter, divided by the value of M is 1 kilogram multiplied by R. The value of R is 287 joule per kilogram per Kelvin. So simplifying this, T1 comes out 348.3 Kelvin. So once we find the value of T1, now we can find easily the value of U1, small u1, that is specific internal energy, and from Joule's law it is equal to CV times T1. So putting the values, U1 will be equal to, the value of CV is 0.718 kilojoule per kilogram per Kelvin into the value of T1 is 348.3 Kelvin. So its value will come out 250.1 kilojoule per kilogram. So this is the required value of U1 which we have to find. Now second, to find the value of H2, that is specific enthalpy. For that, for a perfect gas, we have assumed this, that the air is a perfect gas. So for that we can write that the value of H1 is equal to Cp into T1. So also now the value of H1 will be equal to, the value of Cp is 1.005 kilojoule per kilogram per Kelvin into T1 is 348.3. So multiplying this we get 350.1 kilojoule per kilogram. So this is the value of H1 required. Second, for finding the value of volume, before finding the value of V2 we will need some other values, that is the value of T2. So to find the value of T2, for that we will use again the Joule's law, that is U2 is equal to CV T2. Here the value of U2 is equal to, this is 250.1, and its value increases, and it is given over here that at state 2 its value increased by 120 kilojoule per kilogram, because we are talking for 1 kilogram of air, so it will be summed with this. So the value of U2 will be equal to 370.1 kilojoule per kilogram. Now from this we can rearrange it for T2. T2 will be equal to U2 by CV. So putting the values, T2 is equal to, the value of U2 is 370.1 kilojoule per kilogram divided by CV. So CV is 0.718 kilojoule per kilogram per Kelvin. So T2 value comes out 515.5 Kelvin. Now it's easy to find the value of V2 again using the characteristic equation of state, that is PV is equal to MRT. So we are talking about state 2, so this will be P2, this will be V2, M is constant, R is constant, and this will be T2. So now we are interested to find the value of new volume, that is V2. So it will become MRT2 divided by P2. So putting the values, V2 will be equal to, the value of M is 1 kilogram, the value of R is 287 joule per kilogram per Kelvin, and the value of T2 is 515.5 Kelvin, and the value of P2 is 50 bar. So converting it to Pascal, we will multiply 10 raised to power 5 with this. So when we simplify this, we get 0.0296 cubic meter. So this is the required new volume for state 2, and it is the overall solution of problem 2.8. Thanks for watching. Please like and comment on my videos. Also subscribe my channel to get new videos.